I introduce Dr. Lenin Babu. I just met him. He's a very humble person and an excellent teacher also. He is professor and HOD at JIPMER, and he is a life member in Indian Society of Anaesthesiology, life member of Aura, life member in ISSP, member of IARS, Research Society of Anaesthesiology and Clinical Pharmacology, Association of Obstetric Anaesthesiology. Also is the office bearer of Puducherry State Branch President-elect. Selected publications and papers, several international and national publications indexed in PubMed. Awards, Best Reviewer in IJA 2018. Field of interest, regional anesthesia, pain medicine and transplant. We have got an apt person for an apt subject. Sir, wish you all the best. Go ahead, sir. Thank you.
Okay. Thank you very much for the kind introduction, sir. It's a difficult session after the lunch. Okay. As many of us feel that the physics is most uninterested and boring subject, but the organizers have thought of a lot of things and then change the topics to make it more interesting. So I thought maybe because the post-lunch session people didn't turn up, but whoever is presenting, thank you very much and welcome you all for the talk. Okay, so now we are going to talk about the physics and the soap bubble. Okay. Now, yeah. So the soap bubble, we look at the two aspects. One thing is how the soap bubble is formed and what is the physics behind it or what is going to tell us. And the second thing is once the soap bubble is formed, how it is maintained, what is the physics behind it. So based on these two aspects we will see. Okay, and I am sure even though not many on this hall, but each one of us would have played with this soap bubble at some point of time, either with you or with your kids or someone, right? So how it is formed is very easy to understand. So what do? You just blow air to a soap bubble and then the soap bubble forms. Easier. But what it tells, the process what it tells is that you are going to give the flow of air to the soap film. So it is going to tell the relationship between the force and the pressure. So if you look at that, it remains as the Newton's second law, which is force is equal to the mass into acceleration, and then the pressure is by the force divided by the area. So all of you must be having the experience. If you are going to give the same force to a 10 ml syringe, the injector will be going faster. But if you are going to use the same force to a 50 ml syringe, that is going to be less force. That is because the area in which it is going to act. So the same concept we are going to be used in the case of formation of the soap bubble. Now look at this diagram. This nicely the scientific, I took it from the physics journals. So this is the flow of air they gave, and then it goes to the soap film. From there it forms a soap bubble, and this is ultimate formation of soap bubble. So what happens here is there is a formation of the laminar flow is coming from initially, it goes there and then turns into turbulent flow, and then ultimately due to the surface tension it forms as a soap bubble. Now, so before we go actually into the things, we will see how this concept of laminar and turbulent flow. I am sorry for that because the next talk is there about the laminar and turbulent flow. I didn't know at the time of preparation, so sorry for the overlap. So what is laminar flow? Whenever there is a flow occurs across a tube, it follows a different path, means it moves in a layers. The outermost layer it moves slowly and the innermost layer it moves faster. So here it goes several other contributing factors are there. I will not go into detail because it will be dealt in the next lecture. So laminar flow is based on the pressure difference, diameter, viscosity and length. Now if you look at the applications of the laminar flow, so we always choose the larger peripheral cannula for the fluid resuscitation because of the bigger diameter, and we don't prefer the center line because of the longer length based on this formula. Coming to the turbulent flow, as you see in the first diagram how the soap bubble is formed, if the laminar flow is going to come and is going to come to obstruction, there is going to be change of the flow from the laminar to turbulent. Same way, when there is an angulation or when there is a diversion of the flow, at that point the laminar flow changes into the turbulent flow. Again, here is going to based on the velocity, density, diameter and viscosity. So, if you calculate the Reynolds number, the golden numbers are like less than 2000. If it is less than 2000, that is going to be a laminar flow. If it is more than 4000, it is going to be a turbulent flow. In between the 2000 to 4000, it is a mixture of turbulent and laminar flow. Now, before we actually go into the how this laminar flow and turbulent flow is involved or used in the formation of soap bubble, we need to understand these two concepts, how this is applicable to us in a day-to-day life. So, one thing is a tube, another thing is orifice. Whenever the flow of either fluid or gas goes across the one structure where the length is more, then that is a tube. When the diameter is more, that is orifice. So, where this is practically applicable is in our day-to-day life is at the flow meters. If you see here flow meters, when the low flows, when the bobbin is at the bottom of the orifice tube, here if you see the length is more and this is the diameter. So, here the length is more, so here that is a laminar flow. When the flow is increasing, the bobbin goes to the top, and then there if you see the length is smaller compared to the diameter is bigger. So, here it will act as orifice. So, based on these concepts, when a low flows, it acts as a laminar flow, and with the higher flows, it acts as a turbulent flow. That is how we relate that thing. Now, we come back to the soap bubble. Now, what we see until now is there is a flow of air, that is a laminar flow. It comes and hits, this is the soap film. It comes and hits here, causes the turbulent flow. It causes the increase in the pressure, and then due to the surface tension, it forms. So, we need to understand what is surface tension. So, surface tension is, if you define, I am not going to define the definition as such. So, it's basically it's a force what is there acting on the surface of the liquid, and it tends to go to the least possible surface area. The least possible surface area is sphere. So, that is why when we give IV fluids, it forms a drop, or any drug forms a drop, any liquid for that matter, dropping from the tap water or a hanging drop method, anything. So, that is going to form a sphere. So, now that is the surface tension which is going to cause, I will tell in detail bit later. That is the one thing concept of the surface tension based on which the bubble is formed. The second thing is the capillary action. So, this also uses the addition and the surface tension. When the capillary tube is kept at the top of the fluid, because of the additions and surface tension, it tends to go up. Any idea where is this used? Any postgraduates? Can you guess where this capillary action is used in the anesthesia practice? Okay, it is there in the vaporizers, where it is there in the wigs. They use these to increase the surface area. So, that is how this is used. Okay, now we come to the actual soap bubble. It is a formation of 3 layers. Whatever the wall is there, the wall is having a soap bubble and the water molecule and a soap bubble. So, there is going to be interaction between adjacent molecules. The soap bubble will have the interaction with the adjacent soap bubble, the same way the water molecule and the water molecule. So, it is going to be 3 layered formation of the wall. So, the surface tension, it binds them together, and then soap bubble is maintained, and then inside the air is there, and then air is going to give the pressure. So, at some point of time when the bubble is not ruptured, the inside the air bubble and the outside the air bubble, the pressure is going to be maintained. But what is interesting is about the wall tension, the surface tension between the soap molecules and the water molecules. So, this is dealt by the law of Laplace. That is a main concept of the soap bubble. What it tells is it has a relationship between the wall tension to the pressure and the radius, right. So now we look at the law of Laplace. He tells the surface tension is equal to the pressure and radius divided by 2. But we anesthesiologists, we always look in terms of flow and pressure. So if we look at convert the formula to the pressure, that is P is equal to 2T by R. So that's the law of Laplace. Now where this is going to be applicable in clinical practice? We look at the alveoli, where you have one big alveoli, one small alveoli. Due to the differential lung emptying of the alveolus during the expiration, whenever the smaller alveoli, according to the law of Laplace, when there is going to be a smaller radius, the pressure is going to be bigger. So at the end of expiration or close to the end of expiration, all the gas will flow from the smaller alveoli to the larger alveoli, thereby resulting in a atelectasis. But this does not happen practically because of the surfactant. So when there is a newborn where the lack of surfactant in some conditions, there this is applicable, and then that leads to the atelectasis. The second one is at the time of air embolism. Whenever the air travels in the blood vessel, it won't form a sphere, but it forms an ellipsoid structure. So the ellipsoid, the leading edge, this is the leading edge. The leading edge will be having a smaller radius, whereas the behind end will be having a bigger radius. So this, according to the law of Laplace, here the pressure is going to be more. That is the reason when the soap bubble moves from one end to another end, when there is a capillary, pressure keeps on reducing towards the periphery. The moment the pressure is reduced, that time the air bubble just stuck to the capillary wall and then blocks the lumen. That's how the air embolism happens. The third application, which is what we do quite normally in day-to-day practice, we look at the cuff pressure by palpating the inflated pilot balloon. But what normally happens is, it's again the Laplace law is there. So what we palpate the pilot balloon is having a small radius, so it tends to have a higher pressure. And second thing, what we are palpating is not actually the intra pilot balloon pressure, that is the surface tension of the small balloon. So hence whatever we are palpating by the hand, that is not going to be reliable or reflective of the intra-cuff pressure. So that is the reason this is not recommended. We need to use other monitors to look at the intra-cuff pressure. Third thing, this is an interesting picture I got from the internet, where they have given volume of 150 liters in the pressure reservoir bag, and this is having a diameter of 66 centimeters, but the inside pressure was only 34. Again, this is according to Laplace law. Whenever the pressure whenever the radius of the reservoir bag increases, the pressure drop occurs. So that's another practical application. So another one is the dilated cardiomyopathy, where there comes failing left ventricle. Usually we ignore the width of the either hollow cylinder or hollow sphere viscous, but here, because the left ventricle, we need to include the width of the left ventricle also, that is the thickness of the left ventricle. So the law of Laplace states the wall tension is equal to the pressure and radius by the 2. But what we know is the wall stress. Wall stress is the one which is directly related to the oxygen consumption. So that is by the wall tension and the wall thickness. Okay. The final formula is going to be wall stress will be pressure radius divided by the wall thickness. So that's why whenever there is a dilated cardiomyopathy, when the left ventricle becomes thinner and thinner, this wall stress is going to be increasing. So the more thinner the left ventricle, the more it is going to fail. Again, this is based on the law of Laplace. Again, this picture I told, at a given point of time when the bubble is not bursting, the pressure inside the bubble and the outside the bubble is maintained, it's same. Same way, same concept is here, where the pressure below the bobbin and above the bobbin is always constant. That's a constant pressure difference is there. So this remains another principle in our practice. Again, the law of Laplace states two things, one for a sphere, one for the cylinder. Here the same thing for a cylinder also. This applies in case of your aortic aneurysms. When the aneurysm wall bulges and then pressure increases, the wall becomes thinner and thinner, that is going to rupture. That's why the more the diameter, the more chance of rupturing of the aortic aneurysms. Okay. Now here, if you look at the soap bubbles, we always don't see on a single color. It is going to be multiple colors. The color keeps on changing. That is because of the interference. Because I told you the three layers of the wall, soap bubble, soap molecules, water molecule and soap bubble. The ambient light comes and then gets reflected multiple times, and ultimately we get a different colors. So that's because of the interference. So this kind of things comes in the artifact where the ambient light is causing the disturbance in the pulse oximeter reading. This we can remember, that we can correlate that aspect. Same thing for the NIRS monitor. Here also the emitting diode is there, that is goes there and then gets reflected in the brain tissue and then comes back. So the same kind of reflection what happens there in the soap bubble also happens in case of NIRS monitor. So another thing, how the soap bubble ruptures. If you see, the surface tension between the water molecules are less than the soap molecules. So what happens when the surface, as the bubble becomes bigger, when the soap molecule by gravity it tends to come down. So as the soap molecule comes down, the continuity there on the top gets broken. That's the reason this is the microscopic picture of a soap bubble getting burst. So it comes at the top only ruptures first and followed by the other end. You can see the water droplet here, because the water by gravity it comes down. So what actually happens? It comes down and then bursts and becomes separate molecules. So what the rupture of bubble remains as is, whatever starts or whatever comes, it has to come to end. Same way my talk also. So what we learned till now is, we know what is the relation between the force, the laminar flow, turbulent flow and surface tension and the capillary action. All things involved in some or other way to make the soap bubble, and how it is maintained is based on the Laplace law and how it is going to be clinically applicable in our clinical practice. Okay, thank you very much for the patient listening.